In this second episode of the Godot multiplayer tutorial series, I'm going to talk about connecting the client to the server and synchronizing their clocks, which means it'll be able to ensure that the client inputs and the server results happen at almost the same time, or at least if the ping is really bad, we can roll back on the server to the client's requested tick and then simulate the event at that time and see what would have happened if there had been no ping. And likewise, when the server sends a client the information, the client will be able to roll its game state back to the server's tick and simulate what would have happened if the server input had arrived instantly. As you can see, I have designed this very small demo scene, which is not going to be used in this tutorial, but I'm using it to sort of illustrate how the game state manager is going to work. So here's the game state manager. It has just these three static bodies, which are, if you've never used 3D before, it's exactly the same as 2D, except for instead of sprites, we have meshes, which is just the 3D version of a sprite. The character scene, which is just a pill shape with a camera and a hit scan, which obviously will not be necessary in 2D, but this is used for almost every 3D game I can think of for looking at anything or picking stuff up or hitting people or shooting a gun or whatever it is. The server scenes will look almost exactly the same as this, and I'll show you how to convert the client scene to the server scene later on. The script on the game state manager, I currently don't have any code here, but this is what it will do. It will spawn characters in when they connect, and it will free their characters when they disconnect. But of course, that might depend on your logic for when people disconnect, if they have quit the game or if they have just lost connection temporarily or what. It will move every other character throughout the round. So when the server tells this client, hey, everybody else move to these coordinates, the client will say, okay, and then put the local versions of the player in the updated position. And this client's character will not be affected as much, but it will of course have to respond to network events, and we'll talk about that later. Alright, let's get into the code. So I have the client side on the left, obviously, and the server on the right, which I will always have a client on the left, server on the right. So if you ever see code on both sides and you're not sure which is which, client's over here, server's over there. So the first thing is the port. We need to know the port for connecting between both, so they have to be the same on both sides, which is why we will have the same exact line on both sides, and we'll make sure that this number is the same. In the real world, you will have your client have some hard-coded port values that it will connect to for matchmaking servers or something, and then the matchmaking servers will figure out exactly who you should connect to. I'm just using 11,909, but you can pick anything between basically 10,000 and 40,000 and you should be good, but there are some numbers that are reserved. So if you're doing an actual game, you want to make sure that you don't use anything in like below 1024 basically, and then there's some other values that are reserved, but you can check the internet for that and it's not too big of a problem. The next piece is we need to be able to check if the client is connected. So we have a variable with a getter that checks the current multiplayer peer connection status. I'll explain what these things are in a moment. And we have the OK value, which is just this multiplayer peer connection status connected. So it will be 2, I think. Yeah, connection connected is 2. So if the value, the current connection status, is OK, then we are connected to the server. Otherwise, we'll return false, and we can either not process network events or not send it or whatever we need to do. Next, the client has its own ID, which is its peer ID on the network, which I will explain in a minute as well. Last but not least, we have the network variable, which is an eNet multiplayer peer. So Godot provides multiplayer peer, which has different methods like close, disconnect peer, generate unique ID. It has various low-level server stuff. It says high level here, but it's for our purposes, it's low level. You can connect to servers, get the packet mode, peer, channel, but we don't need to worry about these things because we have a higher level version called eNet multiplayer peer. There are other ones that are kind of more complicated in terms of the actual code that you write, which is why eNet multiplayer peer is the easiest one at face value. This means that we can easily create a client and create a server, which are the two things we're going to be using immediately. So this is just the empty eNet multiplayer peer with nothing on it yet, and we will add stuff to it in logic region, which is not RPC stuff. It is just initializing the multiplayer and connecting to the server. First, we connect to IP. So this will be called when the main menu button is clicked or something to connect to the game. So in our implementation here, we'll just have a button that connects directly to the server. But in an actual game, if you're trying to host this on real servers, you would have several or perhaps just one hard-coded IP address along with a port that would connect you to your matchmaking server, and then that matchmaking server would dispatch you to another server, which is not covered in this tutorial series, but I might make another one. So the first step is to initialize the network with create client, and we give it the IP and the port, so it just knows where to go. So we tell it create a client on this side, and then it will go connect to the server. this IP address will probably be your localhost IP address for the majority of your development, and then if you're testing it online, you will put in the IP address of your server, obviously. So then we set the trees multiplayer authority to the network variable. So this is kind of confusing, but the multiplayer variable is a property on every node. So we can see we're in the node docs and we have a multiplayer property. It returns a multiplayer API, which has a couple of functions like get peers. So on the server, we can check all of the clients that we have. We can check is server. We can poll, which we're not going to be using in this tutorial series, but we can request to process the network packets right now. And then we can use this for the default behavior that happens when we call RPC and stuff. So when we RPC something, it will check whoever we're connected to, the multiplayer peer on the multiplayer variable, and then it will go connect to that. Then we just print that we've connected, and we connect the network's variable signals called peer connected to our peer connected functions and our peer disconnected functions. So when a peer connects, we will get the peer ID. We will print the client connected to the server successfully. So here we have activated the multiplayer instance, and here we have actually connected to the server because the multiplayer, actually the network, the eNet multiplayer peer, has emitted the peer connected signal and the peer disconnected signal here. So this will, I'll talk about this in a minute. And peer disconnected, we currently just print that we've disconnected, but you might want to switch back to the main menu or whatever else it is. Then we can talk about the network clock, but first we will fill out the server side. The server side is largely the same as the client. We've still got the port number hard-coded here, but we now have stuff like max players. So as soon as the number of players that have connected to the lobby is equal to this number, we will tell everybody to switch to the game scene, and we will refuse more incoming connections. And I'll show you how we set that up in a second. But there's also something I'd like to mention, which is basically you might want to track if you're running headless or not. So that means that if you're running in the command line or in an actual Godot project. Obviously, when you run a project normally, you've got a window. And if you're hosting it on an actual server, which this tutorial is sort of for if you're trying to host it on a server and like make an actual game that you can host and play with your friends and whatever it is, you probably won't have a graphical user interface. You'll just have the command line. So if you go to the run instances, you can set arguments like -- headless. So if you do this and then run it, we will not see anything in here. It will only show up down there. So this will manifest when you run it as opening a command line window instead of an actual game window. You might want to check this variable, and I'll show you the code that I have in my game for this situation where you're running it headless. You need another thread to make sure that you don't stall the game while you're waiting for input. And then I'm not going to go over this in much detail because you can pretty much just copy it if you need this, but if you don't need to kick players from the command line or change the game from the command line or anything like that, if you just want to run the game and then it does it itself, you can probably set that up without any extra hassle. But if you're trying to do this, you're going to need something like check if the operating system has dedicated server, or if the current display server name is headless, which means that there is no display server at all. Then we get rid of the head, which in my game is a variable in the debug menu that shows all sorts of stats like players connected, pings, game logs. And then in the process function, we update the menu, but not if we're running headless. And then in this other function, get console input, we only poll it every 1000 milliseconds, otherwise we will constantly be running it and it will use a ridiculous amount of CPU. Then we get the input argument with this function, and then if we have one, we handle the command, which just deals with various commands like this. So the input argument starts out as a string. We check if it's not quit. So if it is quit, we'll just leave the game instantly, which you can use instead of Control-C. But this entire thing has kind of been an aside, so there's no need to worry about that unless you want to set up terminal functionality for your game. So the next thing we have over here is our network. Of course, we still have the same eNet multiplayer peer, but we will set it up differently. We also still need our connected status checker, and we will get two functions here for connected clients. So this is a variable we'll be able to easily access that returns the current multiplayer peers, just so that we don't need to call this function everywhere. It returns a packed in 32 array, which is because the clients are stored by ID. So this will return a list of client IDs that are all int 32s in this array. Then we say connected client count, which just returns the size of the connected clients. Then we track the client's ready. So this is how many people have clicked ready up in the lobby, which we'll talk about in a little bit. And then we have our first function, which is ready, which just calls start server. Because of course, as soon as you start the server, you want it to start. This will contain these functions, which I will go over gradually. So I'll do this. So start server, we log it. Then we create a server with on the current port. And of course the IP address will be whatever IP address the server is running on. And here we will put max players, although if you want you could put 12 or something, which will allow any number of people to connect, but we're going to use the max players variable to determine when to switch to the game lobby, which means that you might not want to set the limit of players higher than that, or else more players will be able to connect while the game is playing. But you can play with this however your game is set up. So we'll have max players here. And then we do the same multiplayer peer equals network. And then we connect it to the signals, which are of course these two functions. So peer connected, if the length of connected clients, which is of course updated, we use multiplayer.get peers and then get the size of multiplayer.get peers, which means that we will end up with, if the length of connected clients is the same as max players, we print that we will switch to the lobby screen. So of course we're going to do this next episode because this is just for setting up the connection. Then peer disconnected, we currently just log it, and eventually we'll do that next episode. All right, now that we built out our network server on both sides, we're going to set up the project itself by coming into here, going project, project settings, globals, and then clicking the file icon, finding script, network, network server. We open it up, and now we have network server as an auto load like we discussed in the previous episode. We will also, of course, come into the server and do it the same exact way. And now we have network server as an auto load on both sides. So if I run the project, we will see that we are starting a server on my host IP address with this port, and we have 2 players required for the game. Now if we come into debug, customize run instances on the client, and say enable multiple instances, we can set this to 2. And now on the client, we come into the script and we add a ready function, which just calls connect to IP with localhost for now. So this will connect to our own PC, which is this IP address for me, and then it will of course use the port that we've hard coded, which is already the same as the servers, and then we'll connect to the game. So now that we've got that set up, we can run the client, and we will see both of our windows here, and they've connected to the server. They both have been assigned random user IDs, and we can see that the first one joined, and the second one joined, and then the server realized that the game was full, so it broadcast switching to lobby screen, which is exactly what we expect. And now that the server script is done, we will be able to get to work on the clock synchronization, which will be slightly harder, but it will not be too bad. So, first of all, we have some constants. The FPS should be the exact same as the physics FPS in your project settings. So if you come into physics, common, physics text per second, it should exactly match this value. Whoops, 60. Is the default, and that's what I have it set to in both the server project and the client project, and they should be exactly the same, or else you're going to have pretty big problems with the synchronization. Then we check the milliseconds per frame, which is 1000 milliseconds divided by the FPS value, of course, and then seconds per frame is that value divided by 1000, because there's 1000 milliseconds in 1 second, obviously. Now we'll be able to define the number of milliseconds between pings, so we will ping the server every 500 milliseconds to synchronize the clocks. If we do it too frequently, we'll be using too much bandwidth, and then the clock might jitter a lot. And if we do it too infrequently, then the client and server clocks will desync further than we want them to. We're also going to need a timer variable, which I'll set up in a minute, and we call it underscore ping timer. The underscore represents that we don't want to use this variable from anywhere else. So if I come into here, which I will do anyways, and add NetworkClock as a global, and come back in here. Now if we are a network server and we try to go NetworkClock dot underscore ping timer, we see that has an underscore, which tells us that we shouldn't be using the variable from outside of here. And since Godot doesn't have private variables, you can do this instead. Then we track the milliseconds that the client has been open via underscore client clock milliseconds. So this just returns the get ticks millisecond, but this is a more obvious name, and I'll explain why that's needed in a minute. And then we also track the ticks. The raw client tick is incremented in physics process. That's all physics process does on the clock. It increments the raw client tick. So this tracks, obviously, the exact number of physics frames that have happened since the client was started. this number is meaningless except in reference to the server's tick rate. So the actual client tick is the raw client tick, the number of ticks that have happened since the client has been started, plus the offset between the client and server ticks. So if the server was started 100 ticks before the client, then the client will, after the first couple of pings, they will realize, okay, the server is 100 ticks behind me, so tick offset will be negative 100, and every time the client tick is accessed, it will modify it, which is essentially guessing the exact server tick at the current moment in real life time, even though we don't know exactly because of the ping and delays in the network. This allows us to send the client tick at which an action happened, and then no matter how long it takes to get there, the server will know what tick it needs to simulate to have the most accurate simulation. Now we have a very simple function for setting up the ping timer, which has a safeguard just in case it's called twice, it doesn't do anything. Then we create a new timer, set the wait time to however long we set between pings, and then auto start it as soon as we add it to the scene. Then we will connect the timeout call to request ping, which we'll build in a minute, and then add it as a child of the NetworkClock singleton. Then we have a small helper function for milliseconds to ticks, which divides the millisecond value passed in by the milliseconds per frame. Now, in our requests region, we have request ping, which if we are not connected, as we defined this earlier, remember how that was going to come in useful, we can RPC the server, first ever RPC call, and send it our client clock milliseconds and the client tick that we're on right now. And I'll show you how that works in a moment. Then we have the actual RPCs. So this is the RPC called by the server towards here. And then we have the RPC parity, which is client to server. So I'll explain this after we build the server side because it makes much more sense. The server will also track its own tick and will also increment it in the exact same way as the client. And the client will be trying to guess this value the whole time. Then in the RPCs, we have the server ping function. And of course it's complaining, so we will give it the client pong function, which is reliable. So we actually need to cut this and put it over here as well, of course. And now we have NEP reliable on the server side, NEP reliable on the client side, and reliable, which means that we are all set up. So the server side, you might have noticed, is much simpler because the server just has to worry about its own clock and the client has to worry about both clocks. So in the request ping function, we are sending the current client clock milliseconds and the raw client tick. So the exact tick that is just incremented in physics process. Then in the server, we get the client clock milliseconds that we're going to echo back to the client and the client tick. We use this function, which we will use on most functions on the server side to know who is calling this function, multiplayer.getRemoteSenderID. So if this is the first line in a RPC function, it will return the ID of the client that sent the RPC call. So we don't need to send that in all of our RPCs. We can just use this function on the first line of every RPC function or any RPC function to get the client that sent this packet. Then we will send the data back to CPong, and we will send it to the requesting client only. So notice on the client, we say sping.rpcid 1. This 1 is the ID. You can see that the first argument is peer ID. So the peer ID 1 is the server. Peer ID 0 is all clients, or all connected peers actually. So if on the server we put 0 here, it would send it to all connected clients. But we're putting requesting client ID because we only want to send their ping response to the client that asked for the ping, of course. Then we send these two arguments as well. Now here we send server tick, echo client tick, and echo client clock milliseconds. So if we send the server tick and the echo client tick right now, that will tell the client the exact differential right now, which means that we can calculate the tick offset that we were talking about before. Now in CPong, we receive the server tick as of this ping arriving at the server, the echo client tick, so whenever we sent this message in ticks, and whenever we sent this message in milliseconds. We can calculate the round trip time as the current client clock milliseconds minus the amount before. So now we are further in the future, which means that this will be the differential from then to now, which is the round trip time. The one-way time is milliseconds to ticks, round trip time divided by 2. So we want to calculate the one-way time because then we can determine how long it will take for a packet to get there, and also how long the server packet took to get back, which is the most important number, because then we can calculate client behind ticks as server tick at that time minus echo client tick at the time the server received the data. And then the tick offset is the client behind ticks. So we're behind by this many ticks. And we subtract half the amount of round trip time. And then we know the actual tick offset between the client and the server, which means we'll be able to accurately guess what time it is on the server from the client, even though there's a delay. And by the way, if you are going to build a debug menu with the ping display or something, the RTT value, you can save that in like a variable called like underscore or whatever, most recent ping milliseconds equals RTT. And then you'll be able to track that for your debug menu or for your logs or whatever. So let's add in request ping. We will say requesting ping. On the server, we will say returning ping to client, requesting client ID. And in fact, I can put this on multiple lines. On tick, server tick. And now the last thing we'll do is in the Pong, we will print tick offset, and then we will print the ping. And now just for testing, we will add a ready function, and we will call setup ping timer so that the pings will begin immediately. And now we will start the server. There we go. We will start the client, and we'll open up the output window as well. We can see that they are 2 at a time because there's 2 clients, and we do not see the server responding. Let's find out why. Debugger. Node not found network clock. So that means that we have not set up, which of course we haven't, the network clock. Actually, sorry, I'll do it like this. There's network clock there. And there's network clock there. Now we'll try again. There's our server. That is working much better. We can now see that the servers are returning pings to both clients on every so often ticks. And the clients are printing their values, which seem to be around 13 ping. And the tick offset is about 300, which makes sense because if it is 60 ticks per second, that's about 6 seconds, which is around the difference that it was between when I pressed this button on the server and the button on the client, which means that our clocks are probably synchronized. And let's just find out by changing what we're printing. We will only print server clock as the exact tick that we estimate the server to be. And over here, we will do the same thing. Let's see what happens. They seem to be roughly in sync, but it's hard to tell. So now that we can see that the clocks are indeed being synchronized, we can fix this ready call by instead putting it in NetworkServer. And whenever peer connected happens, we can actually finally do this, which is set up ping timer and request ping. We could just do this, but then it will delay for 500 seconds before we get the first call, which means that we're going to request a ping and then set up the timer right away. So in the client, once we have connected to the server, we will initiate the first ping on the network clock, and then we will ask it to set up the ping timer. So we can't do this before the server is set up because there's no server to ping. And although here we check for this, we might as well only set this up once we are sure that the server exists. Alright, so that pretty much covers everything in the first programming tutorial of this series. I have a couple of things to note, which is that I have used camel case this entire video, which is just my personal preference. I like to do this because I prefer to type it over snake case, and it's very obvious when it's my function versus when it's Godot's function, because it is clearly formatted differently. But if you would like to go with the Godot way of doing things, you can name all these functions in snake case however you'd like, and that's totally fine. Secondly, there's this really weird quirk of Godot's networking where if your server is running in headed mode, so not how I've set it up here, where we have the run instances, where we have it headless here, and now that we have only running in the console instead of running in an actual game window. If you have it running in a game window for your testing or for whatever, then the multiplayer polling will only be polled according to max FPS. So if your max FPS is limited to something like 30, like it was for my game, then you will only receive packets 30 times per second, as opposed to what you probably want, which is 60 times per second, or if you're going even higher, 100 times per second, or whatever it is, which is the same as how frequently you're sending the updates in the client. So make sure this is not set too low for your project. If you only want to process it so often, you could do it like this, but as soon as you go back into headless mode, then you're going to end up with the regular timing anyway, which means that it's kind of pointless to set the max FPS on your server, and obviously in the client the max FPS will be whatever the user can run or whatever they've limited to or anything. So just make sure that you've kept that in mind. And the final thing to mention is that these two projects will both be on a GitHub repo that I've uploaded in the description of the video. There's just going to be a link, and it'll take you to the GitHub for all the episodes separated by client and server and separated by episode. So you'll exactly find the final result of each episode in there. And since you're going to be looking at that, you should also know how I've organized things, which is script has scripts with no relevant scene attached to them. So the network, for example, does not have like a game scene or a player scene or anything that goes with it. So it's just got script, network, and then there are scripts in the network. And I also keep them the exact same on client and server, just to make sure that your brain can read it. And the character and world obviously are just sort of empty-ish template scenes. And for example, the server one is completely empty, and the client one, I have this very small scene that next episode we will be copying to the server and taking out all the meshes and stuff so that it is a server-ready version of the world, so the server can run its own authoritative simulation and there's no cheating. Other than that, thanks for watching and have a wonderful day.